Welcome everyone. Welcome to today's lecture. And today is our second revision class for nuclear and particle physics. So let me again repeat myself. These classes are going to cover from the very basic to the very end. So some student requested me for CSIR net question as well. Yeah, we will reach to that point. Scattering questions, all of those questions will get covered. But we are starting from the beginning. Why we are starting from the beginning? That you will realize today. The reason being because we are only on our second class, and today we are going to discuss 7 questions of CSIR net. So this is one of the most famous topic of CSIR net, from where they have asked many questions in the history. These questions are also being asked in IIT Jam. Sometimes they are also asked in TIFR, and GATE also has asked this question multiple times from this topic. So this topic become the most important topic for us, right? And we will understand it briefly, and what are all the things that are required to know here. In the yesterday's lecture, we understood what is binding energy. So binding energy is energy required to break the nucleus, or basically to form the nucleus. And we saw the graph. We saw that okay, there were magic numbers, then the graph was getting constant, and we explained fission and fusion through it. But that was an experimental result. We obtained that binding energy from an experiment. After that graph came into the publication, many models tried to explain that graph. When I say many models, it basically means that the models are classical models. Then quantum mechanics also played a very important role in explaining that. So it combined, just like an atom. So when an atomic model spectral structure came out, we tried to solve it through the Thomson model, Bohr's model, then Rutherford model, Bohr's model, and then we go for the Schrodinger model. Similarly, is the case here. The difference here is that in our syllabus, or you can say in any academic university syllabus, there is no perfect model which explains that graph entirely, right? Even the quantum mechanical model which we will study, which is shell model, also does not clearly explains that graph properly. But the model, today's model, which is liquid drop model, is a classical model, and this model is a very good approximation to that graph, and that graph will be explained to a very nice way with this model. Okay. But in CSI net syllabus, above liquid drop model is also something called as collective models. So collective models are also important, and yeah, so that also we will cover up how liquid drop model can be extended to a larger extent. But let's come to today's model first. So the scientists began the study by the very simple approximation. Let's assume nucleus is a liquid drop of a liquid. And whenever you try to make some assumptions, you should understand why we can make this assumption. What is the basis of this assumption? On what basis we can say that okay, nucleus is can be thought of as a you can say as a liquid drop. So there are few similarities. For example, in nucleus we have nuclear forces. In liquids we have surface tension. Okay, so forces are there. Then in nucleus we have nucleons, proton and neutron. In molecules we have molecules. In liquid drop we have molecules, water droplets or honey drop, whatever is your drop, right? In nucleus, the density is independent of A. Yesterday we saw that central density was not depending upon the atomic mass, which basically means that central density does not depend upon the size of the nucleus, right? If it is independent of A, you can keep on increasing A. Basically, you can keep on increasing the size of the nucleus, and the density will not change. Similarly, in the water droplet, the density of the water does not change with the size. If you take a small water drop or a big water drop, both cases have the exactly same density. So that is also a very good similarity. Then heat of vaporization. Basically, what here is happening with binding energy, the same thing happens with the thermodynamics of the liquid drop. The radioactivity in which the particles are emitted can be explained by the evaporation. In water, you see there is an evaporation which happens. in nuclear physics, the radioactivity happens. Nucleus breaks and something comes out, right? Absorption. Sometimes nucleus also absorbs the particle. Similarly, in water droplets, condensation happens. It absorbs the moisture and becomes bigger. So you see, there can be many similarities in which we can see the nucleus may be thought of as a liquid rock. Okay, so let's say we go for this model. We say, okay, let's attempt. Okay, how many of you know Leonard from Big Bang Theory? Do you know Leonard from Big Bang Theory? There is a one Sheldon, and Sheldon has a Leonard, right? If you have seen Big Bang Theory, you might be knowing what I'm talking about. So the character of a Leonard is basically uh, motivated from the scientist who developed the liquid robot. Okay, so that you should know it's the, and you might know in the later stages, in the end stage, uh, he also gave a similar model in the show as well, in which the universe can be thought of as a some sort of a I think surface tension or something like that. So Leonard is basically motivated, not exact person, but it was a motivated, as said by the producer, it was motivated. Okay, so this model was very nice and to the point model. What are the assumptions of this? Assumptions of this model is incompressible. So it is incompressible. You cannot compress the liquid. Second, every nucleon experience identical force. So every nucleon is experiencing the same force. So basically, proton, neutron, the force between proton and proton is same. Force between proton and neutron is also same. The force between neutron and neutron is also same. Okay, so there are, that is a kind of situation here. Also, nuclear force saturates. Nuclear force saturates means that every person will exert the force only on the neighboring person. So if I'm here and I will only exert the force to the nucleons which are close to me, which are next neighbors to me. I will not exert the force on someone which is 2 or 3 nucleons away from me, because the nuclear force is a short range force. There is one lecture coming up in which I am just going to cover it, all the nuclear force properties and what does they mean. But for today, you should understand the nuclear force saturates. Every person exerts the force on next neighbor only. Okay, that is a meaning of nuclear force saturates. Then the fourth assumption, which is very simple, is that assume the nucleus to be spherical in shape. Okay, assume, it's an assumption. So based on these 4 assumptions, we develop a model. Okay, how does this model being developed, and what is a critical thinking behind the model? So basically, binding energy is what? Binding energy basically is an energy which binds the nucleus together. Again, I will repeat myself. It is not the energy which a nucleus have. Yesterday we have a long discussion of this. The energy that your nucleus has is something different. Why does your nucleus have an energy? Because if you look at the nucleus, inside that is proton and neutron, and protons and neutrons are doing many things. They might be vibrating, they might be moving, they might be rotating. Because of all those things, your nucleus have an energy. Okay, now second is binding energy, which is the second part of this. Binding energy is basically the energy you need to break the nucleus. And why do you have binding energy? Because nucleons are bind to each other. They are attracted by each other. That is why there is a binding energy which is there. So you need some energy to break it. And whatever energy you need to break it is known as the binding energy. So binding energy is not energy that your nucleus have. Okay, okay, clear. So now we went into the situation where we start imagining who can increase the binding and who can decrease the binding. That is the whole idea. Okay, if we have a binding energy, who is there to increase it? What factors will increase the binding and what factors will decrease the binding? Okay, so there is a question says that something sir, protons and neutrons are held together by strong forces, right? So binding energy and strong forces are same. No, binding, how can energy and force be same thing? Yes, binding energy is coming because of the strong. Okay, so there are strong forces, people are binded together, and in order to break them I need energy. Okay? Energy and force are never the same thing, but yes, binding energy comes because of the force. Okay. Okay. Okay, perfect. So now we will understand which terms increase binding energy and which terms decrease binding energy. The very first term is a volume. Okay. Now, what is volume term? Volume term basically means that, okay, in your entire nucleus, you have many nucleons and all of them are exerting force on each other. So that is a most fundamental term. So we start from the very fundamental term and we call it as a volume term. And why is volume term there? Because of the nuclear force. And since you have a volume, you will have the forces between the nucleons and you will have the binding. Perfect. That makes perfect sense. So how does this term be written? So volume term basically could be imagined as कि binding energy per nucleon remains constant. Okay? And that we saw. Binding energy per nucleon remains constant. How? Because you see the graph, in the middle part of the graph, binding energy per nucleon is constant. But again, let me not manipulate you in this direction because this was an experiment. Now we are on theory. So why I am saying that binding energy per nucleon is constant? Why theory person is saying this? Experimental person says that is makes sense. Ki, okay, in the middle part, the binding energy per nucleon is almost constant. The theory person is saying this because every person is exerting the force on the neighboring person, right? So it does not matter how many people you have in the room, the force acting on each person will remain same. Let me state that again. Let's say there are two categories. There are two scenarios. You are in a classroom, and in classroom, everyone exerts force on everyone else. Okay? Does not matter how far you are sitting or so on. So if you are sitting here, and there is someone who is very far away, that person also exerts force on. So now, how many people are there in the room will decide how much force is acting on you. If there are 100 people, more force will act. 100 people are basically attracting you. Okay. In the second category, which is we have right now, the force is exerted only by the neighbors. And everyone have 3 or 4 neighbors. So let's say you are sitting on a desk and only few people can exert force on you. One who is sitting right of you, who is sitting left on you, who is sitting front of you, and who is sitting back of you. If only 4 people are exerting force on you, it does not matter how big is your classroom. If the total classroom strength is 100 or 200 or 300, it does not matter because only concern is that those 4% for you. That is why binding energy per nucleon is constant. It does not depend upon the A. A basically is the total size of the room, right? Total size of the room, or you can say mass number. If the mass number is big, the size of the nucleus is big. You saw yesterday, right? The radius is equals to R naught A ki power 1/3, right? So if you increase A, the radius also increases. So it does not matter at all what is the total size of your nucleus. B by A will remain constant. And this is happening because nuclear forces are only exerted on the neighboring nucleuses. So this you should remember. Why volume term is significant and why volume term works is because of this. Okay? So if binding energy per nucleon is constant, it basically means binding energy will be directly proportional to A. Okay? Total binding energy will increase because you see, if you have to bind more nucleons, then obviously total bind is, for example, very simple idea. The cost to feed 100 people is 1000. So it means 10 rupees per person. Obviously, cost to feed 200 people will be 2000, but cost per person still remains the same. Okay? Because everyone still is getting the rice and dal, and the cost per plate is still remaining the same. So that is more important parameter. So binding energy per nucleon will remain same, but binding energy obviously will depend upon A. Right? In order to bind bigger nucleus, you need bigger energy. But it does not mean that binding energy per nucleon is changing. Right? So binding energy is directly proportional to A from here. And if you remove this proportionality constant, you will get a constant which we can write it as AV, which is means volume constant, right? And this constant is coming from the experimental data. So you can find the value of this constant using the experiments. Okay? That is why this model is also known as semi-empirical formula. Semi-empirical. So the empirical word is used whenever you have something law which is based on the experiments. So this is half theory, half you can say experiment, because you can write the formula, but the values of constants will come from the experiment. Okay? So it is semi-empirical formula. Clear? Okay. So first term is very clear, that binding energy is AVA. It explains the graph to a very large extent. Only the first term is able to explain the graph to a very large extent. Why? Because in the middle of the graph, the binding energy is almost constant. So why it is almost constant is explained, but it is not exactly constant, right? It is not exactly. So you see, this can be assumed as almost constant, but it is not exactly as a straight line, right? It means there are some other terms as well which are adding to this, some perturbations, right? Now we have to discuss those terms, why we are having not perfect constant, but some variation is there. Some variation is there. Why is that variation? So before I go for the second term, any doubt till this point? Anyone? Okay, now we go for the surface term. So the second observation which was done was a surface. Okay, now people thought, okay, if someone is here, someone is okay. Let's not make this diagram. Let me give you imagination. If someone is sitting in the middle bench, means you are in a room and in the middle bench you are sitting. So obviously there is someone on the right as well, someone on the front as well, someone in the back as well. All four people are available. But if someone is sitting on the very front bench, there is no one above him. Yes, he has someone on back, he has someone on left, he has someone on right, but there is no one in the front of him. It means the force on this person will be less. So whoever is sitting on the boundaries, for example, who is sitting on the back bench, there is no one on the back of him. Okay? Whoever is sitting on the window side, there is no one on the left of him or right of him. So whoever is sitting on the boundaries will have one or two people less who is exerting force on him. Okay. So similarly, the protons and neutrons which are on the boundary of the nucleus have less people exerting force on them. That is why we cannot say that, okay, everyone is getting the same force. People on the surface are not getting the same force, and that will decrease the binding energy. Binding energy basically means how you are binded. But the people who are in the boundaries can very easily escape because they have less amount of forces acting on them. It means it will decrease the overall amount of binding energy. So that is why we say that nucleons on the surface experience less force than the nucleons which are inside. Okay? So hence the binding energy will decrease, and this binding energy will depend upon the area. This term will basically, how much it will decrease depends upon the area. So if area is more, there are more people on the boundaries, and binding energy will decrease even more. But if the area is small, then the less people will be on the boundaries, and hence the binding energy will decrease less. Okay? So binding energy depends upon area, and area of the sphere depends upon 4 pi r square. It depends upon r ka square. And you also know that radius depends upon a ki power minus a ki power 1 by 3. Hence this term depends upon a ki power 2 by 3, because you have to do r ka square. And there you have to add negative sign, because it is telling you that because of this term the binding energy is decreasing. Okay? And this is as, which is basically surface constant, and this will come from the experiment, right? So this is your second term. Any doubt in this one? Clear, everyone? Why do we have the surface term, and what is the formula, and why do we have this formula? Yes, is it clear to all of you? Yes. Anything? Perfect. Can we go on for next one? Okay. Okay, let's go for the next one. So next one is the Coulomb's force. Coulomb. Coulomb term. Now, proton have two kind of forces between them. One is the nuclear force. Protons and protons attract each other because of the nuclear force. Okay? But Proton also repel each other because of the Coulomb force. So because of that Coulomb force, although Coulomb force is much less than the nuclear force, but it is still there, right? So between your protons, you have attraction, but you also have repulsion. So because of that repulsion also, the binding energy will decrease, because you see the attraction decreased, so binding energy decreased, right? Because if there is already, if you have to break someone, if you have to break any classroom, and that classroom also already have a repulsion between them, it is very easy to break them, right? But let's say there is a great amount of unity in that room, it is very difficult to break them, right? So that is what we have. No, net force on proton is not zero. Nuclear force is much stronger than the Coulomb force. So it is not like attraction and repulsion are cancelling. Okay. So yes, there is a repulsion, but repulsion is very small compared to the nuclear force. Okay. So again, this term will also decrease the binding energy. Okay. So what is this term? And this term is actually minus, why minus? Because it is decreasing the binding energy. 3 by 5 z into z minus 1 e square by 4 pi epsilon naught. Okay, this is a formula, you have to remember the formula, no derivation is required here. And another point here is that, okay, you can even simplify this and you can say, okay, let's write this as a Coulomb's constant AC, z into z minus 1 will remain as such. And then you also know that R depends upon A to power 1 by 3. And then you collect all the constants and you call it as AC. This is only one term in which we know the constant. In this constant will not come from the experiment. This constant we know for sure. What is this constant? And AC is actually going to be 0.72 mega electron. So AC is 0.72 mega electron. Okay. If the value of your R naught is 1.2 Fermi, if the value of R naught change, then it can change. Okay. But more or less, this is only the one constant in which we know the value. So AC is 1.2 Fermi meter. Oh, sorry. AC is 0.72 mega electron volt. So that is something we know. So what do we learn in here is that the binding energy decrease because of repulsion between the protons. So if it decreases, so we have to put a negative symbol, and the formula for this is minus 3 by 5 z into z minus 1 e square by 4 pi epsilon naught r. Okay, and that's all. And then you can combine all the constants and call that constant as AC, and you will left is z into z minus 1, and you know r is proportional to a ki power 1 by 3. Yes, any doubt in this one, please? Clear, everyone? Coulomb's term. So we first had the basic term, which was a volume term. And then we saw two people who were reducing the binding energy. One was a surface, because people on the surface experience less force. And the second is a Coulomb term, because there is a Coulombic repulsion. Due to that also, the force will decrease, or the binding energy will decrease. Okay. Then we have is a asymmetry term. Okay. Now it was observed that this is observation. No, to be honest, people did not have a very clear idea why this was happening at that time. Quantum mechanical model gave much better idea, but at that time it was not very clear. But okay, what is this asymmetry term? So it was observed, or it was seen, that the nuclear which are more stable, those nucleuses are more stable which have equal number of proton and neutron. So the nucleus which contains equal protons and equal neutrons will be more stable than someone who is having more neutrons and protons. But this trend does not follows for a larger nuclei. So in you see that okay, helium is 2,4. It means there are two protons and two neutrons. Then lithium is 3,6. There are three protons and three neutrons. Lithium 3,6 is more stable than lithium 3,5. Okay, and that is similarly hydrogen, one proton, one neutron. Sorry, no neutron. Sorry, hydrogen we cannot, because hydrogen is not a bound nucleus, so we cannot take it as an example. But if you talk about the beryllium, 4,8, hydrogen, helium, lithium, yeah, 4,8. This is more stable than this 4,9 or 4,7. These two are not very stable, but this is stable. So for the lighter nucleus, you observe that the doubling rule, right? If the atomic number is 4, mass number will be 8. If the at 3, it is will be 6. So equal number of protons and neutrons whenever we have more stable. Then there are isotopes. You know isotopes. The atomic number is same, but the mass number is different. So 4,9 beryllium is not that stable. 4,7 beryllium is not that stable. 4,8 beryllium is very stable. Okay? So why is that? So basically, this is an observation. But so it means if you have a difference in number of protons and neutrons, asymmetry will come and binding energy will decrease. Basically, stability will decrease. It means this term, first of all, will be negative because asymmetry will bring the instability, and this will depend upon the difference of number of neutrons and protons. Okay? It will depend upon difference of neutrons and protons. And n can be written as a minus z, so it will become a minus 2z because n is nothing but a minus z. Number of neutrons is a minus z. Okay? So one thing is very clear that this term will be negative because asymmetry, whenever the asymmetry is there, asymmetry basically means protons and neutrons are not same. Whenever there will be asymmetry, the instability will increase and binding energy will decrease. If the binding energy decreases, stability also decreases. Okay, perfect. So this term will depend upon the difference in number of protons and neutrons and uska square. Why square? Because more or less the theory I'm not explaining you, but the square is key. It should not matter if you do n minus z or z minus. Okay, it should not matter. That is why there is a square. Okay, anyway. So n can be written as a minus z, so a minus 2z square. So this term you can see here. The numerator is explained. But why there is a denominator? Why there is a in the denominator? The reason being because this fact is not true for the heavy nucleuses. For heavy nucleuses, you know the number of neutrons is much larger than the number of protons. Okay, so why is that? Because when your nucleus become bigger and bigger and bigger, for smaller nucleus it is okay. But if you have a bigger nucleus, now you have a big nucleus, it has so many protons, repulsions are so many repulsions are there because protons are increased. Now there are so many protons. In order to overcome those repulsions, we have to add more neutrons so that equilibrium can be achieved. That is why you see for the larger nucleuses, number of neutrons are usually more. Doubling rule breaks. For example, uranium is 92. Double will be 184. But you see the mass number is 232. Almost 40 more neutrons are there. And even then, uranium is not stable. Right? So for the heavier nucleus, this is a problem. In a heavy nucleus, if your number of neutrons and protons are same, then you have instability. Because then protons will repel each other like crazy, and then the nucleus will break. But that is the idea. So in order to overcome those repulsions, we add more neutrons. So if you have a classroom in which there are a kind of people known as protons, and they fight with each other. So in order to break those fights, you have to put neutrons in the classroom so that they can sit between the protons and the fights can be reduced. Okay? So because if you add more neutrons, the attraction will increase, right? The nuclear attraction will increase. So that will overcome the repulsion. Okay? So that will overcome the repulsion to some extent. So that is why asymmetry is okay for heavier nucleuses, but asymmetry is not okay for lower nucleuses. That is why you see this term is inversely proportional to A, which basically means that if A is very large, then this term will almost go to very less or almost go to 0, or it will decrease significantly. The reason being because for the heavier nucleuses, asymmetry is okay. That is why this asymmetry term, which is B4 term, should decrease for the heavier nucleuses. Because for heavier nucleuses, asymmetry is desired. It is not causing the binding energy to decrease. That is why this term should decrease with the A. If your nucleus size is bigger, asymmetry is okay. So that is why this term should go to 0 or it should decrease. That is why there is an inverse proportionality on A as well. Yes, any doubt here? This term is very important. So there is a negative symbol because this term decreases it. Then it is directly proportional to A minus 2z ka square, because it should depend upon the difference of number of protons and neutrons, which is n minus z or A minus 2z. And it is inversely proportional to A because this term should decrease if your nucleus is big, because asymmetry is accepted when the nucleus is big. Yes. Any doubt? Okay. Then comes the last term, which is pairing term. Now, pairing term is better explained by shell model, but it is also been given in the liquid raw model, and it basically says that even nuclear. Even nuclear means ki number of protons are even, number of neutrons are also even. Even. I'm not saying equal. Even. So maybe the number of protons is 6 and number of neutrons are 8. They are not equal, but they both are even. So when you have even nuclei, the stability is more. When we have odd even nuclei, does not matter. And when we have odd nuclei, stability is very less. Okay? This was an observation, and this observation was better explained by shell model. Okay. So pairing term basically says that even nuclei are much more stable than odd. Odd means ki protons and neutrons both are in odd numbers. Basically, one is 5, one is 7. So this will be very unstable compared to this one. It's not ki okay, pura nucleus will break. No, it is unstable compared to this. Okay, that is okay. So that this term can be written as B5 equals to pairing constant into a ki power minus 3 by 4. This is to you have to be remembered. So if it is even nuclei, then AP should be positive, because even nuclei will increase the binding energy. That is why it should be positive. But if it is odd even, then this is simply 0. Binding energy does not increase, does not decrease. But if it is odd, then the binding energy will decrease. That is why it should be negative. Okay. So this constant can be positive or negative depending on if you have odd or even. Because if you have even, stability will increase. So binding energy will increase because of this. But if you have odd, then stability will decrease. So binding energy will decrease because of this. Okay. So that is your last term, which was pairing. So then we combine all of this term and write the final formula for binding energy, which I think if you go in an exam without remembering this formula, I think this is like a suicide mission. Don't do that. It is a very important formula, very important concept. You should do. So first term, volume term, please note down this formula. And the second term, surface term, there is a negative. Third term, Coulomb term, perfect. Fourth term is asymmetry, proton, neutron not same. Fifth term is pairing term, either nucleus are odd or even. Okay. So 5 terms you need to explain the total binding. So that is why you see the middle graph is not constant. It is varied from constant because of this entire graph. And you can actually, using the computer software, can match your experiment with this formula. And for most of the nucleuses, it will match, and you can find the value of AV, AS, AC, asymmetry, AP. Okay? And there are many papers you will find in which they have done it, and they have given you the values of these constants. Okay? So finding the values of these constants is a experimental. So n minus z ka square is a minus 2z ka whole square, because n is a minus z. Okay. So yes, that is why this thing becomes this. Okay. That's all. That is enough. Perfect. Okay. Chaliye. So this was your formula, and now we will understand the very briefly what was the achievements of this formula. So this formula was very successful in finding the mass and binding energy of the molecules. Finding the the pairing term, it is there, no? So you see, pairing term dependency is on A. Why it is like that? It is not mentioned in the books. It is like an experimental information. Okay, not explained, and it is more explained from the shell model rather than from the binding model. You want the book to understand the physical significance of the power term of A of the fifth term. Okay, if you want to understand that term, you can go for KS Crane. ठीक है, especially you have to go for the shell model. Quantum mechanical calculations will give you some idea. Liquid draw model does not comment too much on this. ठीक है, liquid draw model is basically a model which can be used by the experimentalist. It is a nightmare for the theory people. Okay? So you have to understand that they are just basically a working model for an experimental physicist. That's all. It is nothing more than that. But it is so good for experimentalists that it is widely accepted. Okay. On the other hand, shell model is something which is nightmare for experimentalists, but it is very good for uh, theory people. Quantum mechanics is involved. You take it as an infinite well, and then find out many things. Okay. Chaliye. Okay, so now we go for achievements. It predicts the mass. So mass of the nucleus are predicted very well. Binding energy of the nucleus is not molecules. Binding energy of the nucleus is predicted very well. Not for all the nucleuses. Also, always remember, for most of the nucleuses it works, but there are many nucleuses in this universe, or very common nucleuses even fails to agrees with this model. Okay, so no one knows why. At least I don't know why. Maybe till MSc syllabus, nowhere it is mentioned that why. Okay, at least in common books you can find the reason why, but every nucleus has their own reason. So there is no generalized reason why some nucleuses obeys this and not other nucleuses does not obey this, because it is very very we are not deriving this model from some physical principles. So I did not started with the some physical principle and then I did integration differentiation to get to this form. So it is just like a कि ओके ठीक है, ये चीज इसके ऊपर डिपेंड करेगी, ये चीज उसके ऊपर डिपेंड करेगी, तो मान लो इसके लिए एक टर्म बना दो, इसके लिए एक टर्म बना दो. तो ये बहुत एक्सपेरिमेंटल काइंड ऑफ फॉर्मूला है रेदर देन बीइंग कमिंग फ्रॉम सम प्रिंसिपल्स ऑफ फिजिक्स. ठीक है. ओके, देन सेकंड इज प्रेडिक्ट अल्फा एंड बीटा डीके. अल्फा एंड बीटा डीके एक्सप्लेन किया, व्हाई, हाउ इट एक्सप्लेन. So basically this model says everyone wants to reduce its binding, oh sorry, increase its binding. तो बाइंडिंग एनर्जी को मैक्सिमाइज करना चाहते हैं. So in order to maximize the binding energy, what does nucleus do? Is emit particles. So it will emit particles, and by emitting the particles, it will have the optimized binding energy. That is why you will have a alpha and beta decay. Similarly, in the fission also, so the same thing happens. The nucleus breaks, so fission can also be explained. So breaking of the nucleus could be explained, and it basically explains the motivation of nucleus. Why nucleus is want to break? So it wants to break because it wants to achieve the maximum binding energy. Yesterday we saw that everyone wants to come to the middle of the graph. So that is why alpha and beta decay could be explained from this. Failure of this model was that this model did not comment on the magic numbers. So in the graph very beginning, this thing was also there. So this model was explaining the central part, but not the beginning part where the magic numbers were there. So this model did not explain that. This model did not explain the spin and magnetic moments. That was also important. And this model did not explain the excited states. Nucleus also goes to excited states, and then their binding energies changes. How that does happen, that is not explained, because in this they do not talk about the energy levels. It is not explained that okay, if you want to change according to this model, if you want to change the energy of the nucleus, you have to break it, or you have to combine it or break it. So basically you have to change A and Z. Without changing A and Z, how can you increase the energy or decrease the energy? For example, in a hydrogen atom. So one idea is okay, hydrogen and chlorine combines together makes HCl, and HCl has a different energy than hydrogen and chlorine. That makes sense. But within hydrogen also there are many energy levels. So without hydrogen changing itself, it can also change its energy. That is not being added in this model. Okay? So that is also one idea. It does not explain the excited states. Okay? So that is all about your shell liquid draw model. I will go for the problems now. Any doubt you have in liquid draw model, I give you 1 or 2 minutes, and then you can ask, and then we go for the problems. So I will do 2 questions. There are total 7. I will do 2 questions. All 7 are exactly same. Okay, 7 questions are exactly same. CSIR net has asked 7 questions, which I could find in last few years. They are same, but I will do 2 questions completely in front of you. I will solve, and then you can do other 5 as your homework. Okay. So let's do it. Let's understand. And these kind of questions are asked a lot. Of the nuclei of mass number A, 125. So you have a nuclei. One thing which is for sure mentioned is that mass number of this is 120. The binding energy is calculated from the liquid drop. Okay, so I will respect and I will write the formula of binding energy. So I will very quickly say it is AV into A minus AS into A ki power 2 by 3 minus AC into Z minus 1 divided by A ki power 1 by 3. And then I have plus, minus asymmetry term, which is asymmetry A minus 2Z whole square divided by A. Pairing term we add whenever it is required. More or less, most of the time we deal with the first four terms. One thing is very sure that A is 125 and we are finding the binding energy using the binding energy formula. Some things are given. For example, the coefficients of Coulomb is given. So basically the value of AC is given, which is 0.7 mega electron volt. You see, the values of these constants will be given. Asymmetry is also given. So asymmetry term is also given, which is 22.5 mega electron volt. Okay. Then what they're asking is that out of these four options, for which of the nucleus binding energy is maximum? Basically, all of these are the isobars. Isobars are those nucleuses. Isobars are those nucleuses which have the same A, same value of A. So all the four options, instead of B, all the four options have all the three options have the exactly same A. A is 125. But the atomic number is different. So which of them will have the most stability or the maximum binding? So we want to maximize B. B we want to maximize with respect to Z because we cannot change A. A is 125. What we can change is Z. So we want to maximize B with respect to Z, and whenever we have to find maximum minimum, we do curly B by curly Z equals to 0. Okay. So that this is how we find maximum. Whenever we have to maximize Y with respect to X, so what we say? We say the derivative of Y with respect to X is 0. Okay. So let's do that. So let's differentiate. So curly B by curly Z, if I find out, first term does not contain any Z, so it is 0. Second term does not contain any Z, so it is 0. Third term do contain a Z. So it will be Z square minus Z, so which will be 2Z minus 1. Differentiation of this. Fourth term also contains Z, so minus 2 comes in front. Asymmetry is there. And then you have A, right? And then you can write A minus 2Z. And then using the chain rule, you have to do the differentiation of this also. So you will get minus 2. Okay. So this will be equals to 0. I hope everyone understands the differentiation. That's all. And then you can take this term on other side. Okay. So if you do that, you will get this negative and negative will cancel. So you get 4 into asymmetry term into A minus 2Z by A is equals to A Coulombic 2Z minus 1 by A 1 by 3. Okay. Now it is your responsibility. I am not going to go beyond this. It is your responsibility to solve this out and find the value of Z. This is a mathematics you have to optimize. In an exam, don't think in exam में जाके आप कर लेंगे. No. You have to try this out for all the 7 problems. You have to optimize कि मैं in which way I am going to redistribute my terms so that I get a best answer. My idea is that you put the value of A later on. First, what you do is you put a value of asymmetry, which is what 22.5, right? So 22.5 you put here. A को बाद में देखते हैं. We will put A later on. And then A Coulomb is what 0.7. And then just take A on one side. So क्या करेंगे is if I bring this A on other side, so A1 minus 1 by 3 will become A2 by 3. Okay, so that is also okay, perfectly done. And then I can just take this A2 by 3 on other side, and 22.5 into 4 will give you what? 90. Okay, so this will be 90. 90 na, 22 into 4 88, and 0.4 into 5 is 2, so 88 plus 2 is 90. Okay, and then you write a minus 2z, and then 0.7, so which is basically I can even multiply this, so I will get 1.4 z. Okay, 1.4 z, yeah, abhi 0.7 we can keep outside. 2z minus 1 into a 2 by 3. Okay, again little bit more simplification happens. So 125, so basically what will this give you? 125 की power 2 by 3. So I can write this as 5 का cube की power 2 by 3. So 5, 3 and 3 cancel, 5 का square will be 25. ठीक है, so 90 into a minus 2z equals to 0.7, 2z minus 1, and this is 25. 25. Okay, now even I can simplify more. I can cancel with 5 and 5, so this will become 18 and this will become 5. Okay, and this will become 18 into a minus 2z, and this will become 3.5 2z minus 1. Now it is much easier to solve, right? Because now what you can do very simply is 18a minus 36z equals to 7z 7z minus 3.5. 7z minus 3.5. Okay, so now you can bring this z on other side, so you will get 43z 18a plus 3.5. 3.5. So 18a plus 3.5 you can do. A you know already, right? What is a? So a is 125. So a is 125 plus 3.5 divided by 43. So I am getting is 52.4. So you see option C. 52.4 gives you options. Okay, that's all. That is the idea. Perfect. So you have to be very close to 52.4. The closest answer to 52.4 is C. So this is how you solve the problem. Okay, so any doubt in this one? It was a simple problem. Yes, anything I can help with, any calculation or any general theory. Yeah, done. Clear? समझ गए सभी?
Yes, sir.
There is one formula. फॉर्मूला क्यों लगाना है यार, ये मतलब इसमें आई डोंट नो एनी फॉर्मूला. बाइंडिंग एनर्जी का फॉर्मूला है, वहीं से कर लेते हैं. Okay, then we have this idea. Second question, again you will see the similar category. The binding energy of the light nuclei in mega electron volt is given approximately by. So this time they gave you the form. Okay, now you know the first term is volume term. It means the value of AV is 16. Second is surface term. It means AS is 20. Third term is Coulomb's term, right? Fourth term is the earth symmetry term. So it means A symmetry is 30. Okay, they gave you that. Okay, they gave you that. I think, okay, they gave you that. However, there here should be negative, but I think they gave you the formula, so we will accept this, whatever they have given. Okay, okay. The value of Z is most stable for which isobar? Isobar. It means this time what is fixed? This time Z is fixed. And you have to decide for which value of A the stability will be maximum. Stability maximum means binding energy is maximum. So now we want to maximize B, not with respect to Z, but with respect to A. Because now we cannot change Z, because it is now isobar. Isobar mein Z cannot be changed. Okay? Okay. Okay, perfectly fine. No, it is not C. This is answer A. Answer to this problem is A. Okay, that is the idea. It is not net A or B. Okay, chaliye. Let's talk about this. So we will do curly B by curly A equals to 0. So let's start differentiating. So if I do, I will get first term का differentiation will be 16, second का will be 2 by 3, 20 तो ऐसे ही लिखेंगे, and I will get a की power -1/3, and then third में 3/4 z square, and then -1/3 comes as such, and it will become -4/3, and then you have 60. Okay, now this term, first of all, we can write in terms of a minus z, right? So n can be written as a minus z, so this term will become a minus 2z का whole square. Okay, so treat it like that. So 32 will come in front, so it will become 60, and a minus 2z will become as such, and if you differentiate this with a, it will be 1. Now you have to make this equals to 0. So this term, पेयरिंग टर्म तभी ऐड किया जाता है जब कुछ बहुत मेंशन किया जाए. पेयरिंग टर्म को यूजुअली वी डू नॉट ऐड. ओके, बाइंडिंग एनर्जी का मोस्ट ऑफ द फॉर्मूला फॉर दिस काइंड ऑफ प्रॉब्लम्स इज दिस. ओके, पेयरिंग टर्म कभी कभी कुछ पेयरिंग पे ही क्वेश्चन आ जाएगा, तब आप ऐड करिए उसको. ठीक है, आप देख लीजिए जो फॉर्मूला उन्होंने भी दिया उसमें पेयरिंग ऐड नहीं की. चलिए, अभी क्या करना है, नाउ वी हैव टू फाइंड अ परफेक्ट ए. सो नाउ अगेन इट इज अ सॉल्विंग प्रॉब्लम, सो लेट्स डू इट. थोड़ा बहुत आई एम शोइंग यू मैथ्स सो दैट यू कैन हैव एन आइडिया कि कैसे किया जा सकता है. तो पहले तो सिंप्लीफाई करते हैं. a minus 1/3. Okay, so 3 and 3 cancels here, and it becomes plus, so it becomes z square by 4, a minus 4/3, and then 60 by a minus 2z equals to 0. So basically I need to separate all the terms of a and all the other terms. So पहले तो मैं a की terms को separate करना start करता हूँ, in which I have a, the terms which I have a. If I open this term here only, so I will get 60 because a and a will cancel, right? You see, if I multiply this, a and a will cancel, and you will get minus 120 z by a. ठीक है, so first constant term is 60 plus 16, which is 76. Okay, I'm still doubtful कि here I should have negative, maybe there is a misprint or something here, but ठीक है, I'm not going against the formula mentioned, but I think here should we have negative. But anyway, okay, then what else now? So basically these are in negative. Okay, everything is in negative, so this should be written as a minus 1. Every term is in denominator. ठीक है, if you want you can even write in denominators, that is also. Isobar a fix, yes, isobar a fix, then uh, isobar isobar में तो a fix हुआ ना.
Yes,
oh
sir.
shit,
It's fixed now.
so this is the same question. So they are saying what is the value of z for a most stable isobar. Oh sorry, आइसोबार में ए ही फिक्स्ड हुआ एंड वी वांट टू नो जेड. सो अगेन वही चीज करनी थी, कर्ली बाय बी बाय कर्ली जेड को ही जीरो करना था. एंड देन आई थिंक नाउ यू कैन डू द कैलकुलेशन, है ना, कर्ली बी बाय कर्ली जेड यू कैन डू, तो इट विल एग्जैक्ट सेम क्वेश्चन. तो अगेन डू कर्ली बी बाय कर्ली जेड. सो फर्स्ट में कोई जेड नहीं है, जीरो. सेकंड में कोई जेड नहीं है, जीरो. तो इसमें जेड है, तो व्हाट विल यू से 3/4 इंटू 2z इंटू ए की पावर -1/3. जल्दी से कर लेते हैं, 30/a. इसको हम a minus 2z लेकर चल रहे हैं, तो 2 विल कम आगे, सो इट विल बी a minus 2z, एंड देन वी हैव -2. दैट्स इट. इसको जीरो कर लेते हैं, एंड देन जस्ट सॉल्व. इसको सॉल्व करके व्हाट विल यू गेट इज द वैल्यू ऑफ z, कि किस वैल्यू ऑफ z के लिए काम करना है. ठीक है, ओके. ये क्वेश्चन अच्छा था, इसको मैं करना चाहता था. तो या let ES denote the contribution of surface energy per nucleon in the liquid drop. देखिए कितना सिंपल एंड सिंप्लीफाइड क्वेश्चन है. सो ES इज द कंट्रीब्यूशन ऑफ द सरफेस एनर्जी. ओके, ठीक है, तो क्या होता है फॉर्मूला सरफेस एनर्जी का? ए सरफेस ए की पावर 2 बाई इन द लिक्विड ड्रॉप मॉडल. तो ऑब्वियसली लिक्विड ड्रॉप मॉडल है, तो देन दे से फाइंड द रेशियो ऑफ दिस एंड दिस. सो रेशियो ऑफ 27 एल्यूमिनियम divided by the ratio of 64 zinc will be 27 की पावर 2/3 divided by 64 की पावर 2/3. So this will be 3 का cube, 3 का cube cancel, then you have to square, so this get 9, and this is 4 का cube, 4 का cube cancel, and 4 का square becomes 16. क्या चल रहा है भाई?
per nucleon बोला.
per nucleon है, so here you also have per nucleon है, तो it's not only the surface energy but per nucleon.
-1/3.
हाँ, तो per nucleon में क्या होगा, you have to divide by a. तो अगर मैं यहाँ पे डिवाइड बाय ए करूँ तो वो हो जाएगा, बेसिकली डिवाइड बाय ए करने से क्या होगा, दिस विल बिकम ए की पावर -1/3, which will be as by a1/3. So it will be 27 की power 1/3 and this will be 64 की power 1/3. So this will be 4 and this will be 3, which is your option number B. ठीक है. So this is your surface energy, but this is your surface energy per nucleon. Per nucleon means you have to divide by. ठीक है. So that is how you have to solve the questions. You can see all of them are very similar. So you see then the most stable isobar is, again they are asking the value of Z and binding energy formula is given. Okay, let's see the next problem. Again you see Z by A for the most stable isobar. Again the formula is given. Okay, and then this question, the difference, okay, this can be, we can see the difference in the Coulomb's energy between the mirror nucleus. So what is the difference between these, between the Coulomb energy is given, it is actually given. Assuming that nuclei have a spherical symmetric charge distribution and then E square is approximately like this, what is the radius of this? इसका radius क्या होगा? ठीक है. What is the radius for this? Difference in the Coulomb's energy. What is Coulomb's energy formula? Coulomb's energy formula is Z into Z minus 1, A 1/3. Okay. If I find Z into Z minus 1 for this, I get 24 into 23. For this, I get 25 into 24. ठीक है. You can clearly see that A is same for both. A is same for both. Okay, so A is same for both. So if I find the difference in their energies, so AC by A 1/3 will be common. This minus this, it means 24 into 24 minus 24 into 23. Very smartly, what I can do is ki what I can do is 24 I can take common, and then I will be left is 25 minus 23, which is 2. Okay, and this difference is given to you. This difference is 6 mega electron. You know what is AC, A coulomb, right? A coulomb, you know, right? 3/5 by 1 by 4 by epsilon naught R, E square by R, right? And यहाँ से आपका क्या आ रहा है 48, and यहाँ से आपका क्या आ रहा है 6 mega electron. Now let's see what is given. They are saying that E square is 1 mega electron volt Fermi meter. तो E square की ये वैल्यू है, तो ओके ठीक है, तो E square की you can put the value. You know what is 1 by 4 by epsilon naught, 9 into 10 की power 9. एंड इसको आपको क्या पुट करना है 1 मेगा इलेक्ट्रॉन वोल्ट इनटू फर्मी मीटर, एंड ओके दिस इज can be cancelled and this will be 12. This is 1, and then in the denominator you have R, and R I can take on other side. So solving this will give you the value of radius. Solving this will give you the value of radius. The value of radius will be same for both because radius depends upon A की power 1/3 and A is same for both. ठीक है. So solving this will give you the value of radius. Okay? The answer to this question is D. You can verify that. Okay. And then the last question again is the similar. What is the most stable isobar? Again, you have to choose one, do the maths and get an answer. So these are your 7 problems which could be similarly solved in a way. Whatever was a different or varied question, I solved that for you. Okay. So now is a good time for a DPP. So today, after our second class, I will make a DPP and share it with you, in which we have the basic questions and of the basic nuclear properties and the liquid drop. Okay. So that's all for today's lecture, and now I will meet you all at 7:30 p.m. with our third lecture on electronics revision. Okay.